First, welcome to Seviveli Kalvi channel. Today, let us see the design of 3-bit synchronous counter. So, this is up counter, 3-bit synchronous up counter concept. State diagram can be represented like this. So, this is the initial state. Here, this 3-bit synchronous up counter can be designed with the help of any kind of flip-flop like D flip-flop, T flip-flop, JK flip-flop, etc. So in this example, here I have drawn the state diagram for 3-bit synchronous counter. So if you take 3 bits, our state values must represent in the form of binary values 3 digits. So 000 is the initial state for this 3-bit synchronous up counter. So after that it will be incremented by 1. So the state value is now increased by 001. Again it is increased by 1, 0, 1, 0, and again it is increased by 1, 0, 1, 1. Next 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So once the state 1, 1, 1 reached, again the state goes to the initial state or initial condition 0, 0, 0. So continuously this loop is followed until the execution of the program. When we stop the program, automatically the counter will stop the output. So this is the fundamental concept of design of 3-bit synchronous up counter. So here in the state diagram, the state values are represented. So this is the truth table for 3-bit counter. So we can consider any clock pulse, that is falling edge or rising edge clock pulse can be considered. So in initial condition, there is no clock applied to the counter. So the output of counters will be 3 bits, that is denoted by QA, QB and QC. These three are the output of the 3-bit synchronous counter. So for initial condition, there is no clock applied to this counter. So all the three output is 0. The corresponding decimal equivalent value mentioned as 0. So whenever you apply the first clock pulse, automatically now the state start from incremented by 1. So from initial state 0, 0, 0, it is increased by 1. So 0, 0, 1 state is reached. So because of applying first clock pulse, the output of the synchronous counter becomes 0, 0, 1. So the corresponding equivalent decimal value denoted as 1. And the second clock pulse is applied, again it is incremented by 1, 0, 1, 0. The corresponding equivalent decimal value 2. Again increase by 1, 0, 1, 1, 3. Again increased by 1, 1, 0, 0. 101, 110, 111. So until the seventh decimal equivalent value occurred, that is the 111 of state values occurred. This is continuously going, and once the seventh clock pulse is completed and applied properly to this counter, again it goes to the initial condition or starting state of this 0, 0, 0. So this is continuously going on. So for 3-bit counter, there are totally 8 states are available from 0 to 7. So that states can be represented as, in terms of variable, means S0, S1, S2, S3, S4, S5, S6, S7. Otherwise, simply we can represent that state values by 3-bit of values 0, 0, 0, 0, 0, 1, 0, 1, 0 till 111. So this is the basic concept behind the design of 3-bit up counter. That is, it is a synchronous counter. So let us move to the programming area. So by using Modelsim, I am going to compile this Verilog program. So here I am going to write the Verilog program for the 3-bit synchronous counter. First go to Modelsim software and select file, new, and select source, and after that select the Verilog. So now the programming area will appear in this window. So in this area you can write the source code. So already I have copied my program. So I just open that program and save it here. I will explain all the concept. So this is my already returned program. So I just place it. So here we can see the concept of this program in Verilog model. So first of all, we have to start this Verilog program with starting of module. So that is represented here. After that, we have to give the module name. Here I am representing binary synchronous up counter. So for this BAN underscore synchronous can be represented by short name SYN and underscore up counter. Within this bracket, we have to mention the different variables name which is used in this program. So here I take clock, reset and count. So this clock is one kind of signal and reset is another signal, count also another input. So these are the different kind of variables we have assigned here. And out of this clock, reset, count, we have to mention which can act as a input signal and which is act as a output signal. So for that, here we can represent input. So here the clock and reset is act as a input. So clock comma reset should be included in input area, and I can consider my output variable. So output register. So with the help of this register only I can do the counting operation. That is here within the square bracket, that is array, I have to mention my count values, that is how many number of bit of counters is going to design. Here I am going to design 3-bit counter. For this 2 colon 0 is taken here. That means 2 down 0. So this can be represented within the square bracket. And nearby this, I have to mention the count value. That is the count variable is added. And put a semicolon. And I have to add always at pause edge clock. So now I have written this program in behavioral model. So I have to start with this program with always. At here I have to give this clock pulse in terms of positive edge. So pause edge clock should be mentioned within the parenthesis. And after that, whenever you start with the always, it should start with begin. So in begin, we have to give the condition, that is if reset value is equal to 1. So reset goes high, the count value which is equal to 3 digits of binary value, that is represented by 3 dash B triple zero. Else, when this condition is not satisfied, we move to else. Count is equal to count plus 3 bit of binary value 001. So simply we can represent this value. So this is your initial condition, that is 000, that is your state value. When the reset value is high, your count value becomes 000. If the reset value is not equal 1, automatically it will be incremented by 1. So now you have to end your program because of behavioral model. So this begin is now end with this syntax end, and now the entire programming concept is over. So you have to close your module. So for this you just write a end module here. So this is your program for Verilog concept for 3-bit synchronous counter. Let us compile this program and simulate it. After that we will show the output here. So go to compile. So before this, we have to save this file. So just go to file, save as. So the saved location will be appear here. So here I can give synchronous counter. So for this sync count dot b. So the program should be Verilog. The format of extension file is dot v. So sync count dot v. I have taken as a name, that is file name, which is appeared in this programming area, which is saved as in Verilog module. So after that, go to compile and you just compile it. So sync count, that is your file name is appeared here. So this sync counter.v is already I have written this program, but now I have changed my program name is sync count. That sync count.v file should be selected here and compile it. So in this, some unexpected error is there, I think. So we have to check near equal syntax error. We can check it now. So now I consider this program and again I compile it. So sync counter.v. So here the double equals symbol should be written. Otherwise, it will show as the output. It will not create a proper output. That is, it will show the error. So in case if you put a single equal symbol, your program will not run properly. That is compiled properly. So now instead of single equal symbol, you have to substitute a double equal. Now you can able to compile your program. So compile syncount.v. Now the compilation is over. You just close this window and go to simulate and start simulate. So in this start simulate, the work file is appear here. Here I have mentioned my module name is bin underscore sync up counter. That file module name is appear here. You have to select it and press OK. Now the simulation process also over and the corresponding file is appeared in this area. Now you have to select this. Now you can go for this bin underscore sync up counter. Left click it and go to add to wave and all items in region. Now the wave form window will appear here. Now you can expand it. So here you can use clock is one input signal, reset is another input signal, and count is your one of the output. So here you have to give clock. So right click it and select clock. So in this clock, 50 percentage of duty cycle should be defaultly set by this window. You no need to change it. So both on time and off time of the pulse signal should be represented as 50%. That is equal time period. For that here we have to represent 50 and the total period is 100 and logic value for 1 is selected as high and for 0 selected as low. Here if you want to give rising edge or falling edge, anything can be chosen. Now I choose falling edge and click OK, and after that you can give reset value as 1. So this is the condition we have already given in the program. So after this setting this value, now you can run the program. So you will get the output like this. So in the initial condition, we have given reset value is equal to 1. At the time your initial state value 000 is appear. This can be shown in this waveform window. Now again you have to go for this clock. So again you have to change this clock value by falling edge because already I have selected the falling edge. So again I can select falling edge and I can change the reset value by 0 now instead of 1. And again you can go for run. So now you have seen the second value. So the clock period is in 50 percentage of duty cycle. It is in falling edge clock signal. At the same time, in initially reset value is high. At the time your present state value is initial state and the counter output will be 000. Once the reset value goes 0, the because of second clock pulse it moves to the next state of the output 001. Again you can set reset value which is equal to 0 and put OK and again give clock signal and select falling edge OK. Again you can run it. So after running this, you will get the output 0, 1, 0. Similarly, you can do this operation continuously until you have to apply the 7 clock pulses. Here I can choose it. So here I again select reset value 0, set this value and OK, and again clock is selected as falling edge, OK, and run this. Again you will get the output 0, 1, 1. Now 4 clock pulse is over. Initial clock pulse, additionally 3 clock pulse state is over. Now you can move for another condition. Again clock, select falling edge and again reset, value is equal to 0. Put OK. Again run the program. You will get output 100. So again you go to reset value which is equal to 0. And again clock, falling edge and again simulate, run it. You will get output 101. And next case again set reset value as 0. Again clock pulse, select as falling edge and run it. You will get the output 110. And this is the sixth pulse. So at last condition again set reset value as 0 and clock as falling edge. Again run it. Finally you will get 111 condition. So this is the output of synchronous counter for all states. So in initial state it is start with 000 and after that 001, 010, 011. Likewise every individual state outputs can be present in this waveform window. So I hope everyone understand this concept clearly. So you can do the program by using this Modelsim, and it is a Verilog program. If you have any doubt, you can see it clearly and you can ask me at any time if you have any doubt. Thank you all. Thank you for watching this video and support my channel. Subscribe my channel. Thank you.